So yeah, well, hello all. Welcome to this session where I'm going to talk about power estimation for edge data centers. So a bit of background about the edge architecture. As you may already know, in the recent years, computation has been moved closer to the edge devices, especially for applications that are sensitive to low response times. So we created an extra layer, namely the fog layer between the IoT devices and the cloud layer, which lives close to the end devices. And within this layer, we can find the so-called edge data centers. So in a scenario like this one, what we would like to do is to measure the energy consumption that happens in contrast to the primitive architecture where the edge devices have been communicating directly to the cloud layer. So some reasons why it's important to measure the energy consumption for such data centers will be, of course, to reduce the environmental impact and the CO2 footprint of such data center operations, to reduce the overall energy costs while maintaining the overall performance of the data center. As you may know, energy is one of the most important operational costs of a data center. And according to this article over here, it is estimated that by 2025, 1/5 of the world's power supply will be allocated to the data centers all around the world and the end users. Of course, it will be important to understand the energy demands for multiple workloads that are executed on the data centers, and where available to understand how renewable energy would be beneficial. So in order to measure the power and energy on such a DC, this can be achieved on multiple levels. So on top level, we can have the energy consumption of the whole DC by checking the power meter that is allocated to the DC itself. So within the DC, we can find multiple racks of servers which are getting energy by the so-called power distribution units, and we can get some information about the energy consumption of the rack itself through the PDU. And of course, there are some hardware and software tools that can measure energy. For hardware, it's typical smart plugs you can find in the market, where you can plug an electrical device on it, and you can just call the API or the user interface to grab those measurements. And of course, on software level, there are some tools that they can provide estimates for power consumption at the granularity of a process. I'm writing some tools over here, and there is a survey by Stefanos Georgiou in the end, which analyzes those software tools in great detail. So in order to be able to get measurements about energy production and consumption on a type of DC like this one. Some previous researchers in our lab, they created a platform called NAV, which is an energy monitoring platform for green edge data centers, and they provides information about the photovoltaic energy production that is installed on top of the data center, about weather conditions through sensors that are also installed on top of the data center, and the power consumption of cluster nodes and the cooling equipment of the data center. The initial idea of the project was to create a federation of data centers that belong to NAV, and which will give you the opportunity to distribute workload in real time based on the follow the sun approach, where you distribute the workload where there is more power generation, actually. And it consists of 3 layers. On the lowest layer, the infrastructure layer, you can find the different sensors and bare metal servers, which provide the information about the energy consumption. And those information are stored in the storage layer, where there is a time series database that stores the data. And on top of that, there is a platform layer where there are multiple monitoring and analysis tools and decision-making module, which is not yet implemented for now. Of course, on this layer, there is a graphical user interface where the users can view the retrieved results on their screen. So I created a diagram that illustrates the architecture of NAV. So basically, as you can see in the center, we have a rack of multiple bare metal servers. So within each physical server, there is a set of containers running simultaneously and virtual machines, and each server is connected to a PDU, and through the PDU, so we have a net data agent in each server, which collects the power consumption information through the SNMP protocol. So for the cooling equipment, in which case it's an AC, there is a separate PDU that communicates the results for the power consumption to an AC agent that has net data installed on it in the same way. And there is a third type of agent for the energy production that retrieves the results from the PV system on top of the data center. So all the results are propagated to the Prometheus DB that exists in the storage layer. And so Prometheus pulls this data from the different agents via HTTP calls, which happen at specific time intervals. So in order to be able to identify where those agents are, Prometheus makes use of Consul for service discovery, and there is a graphical user interface on the top layer, which gets the data from Prometheus via HTTP calls. So on this architecture, you can see that we can measure the energy at some points. But what we are interested to do is to measure the energy for individual containers and VMs, so as to have a good idea of the energy demands of each one of them, and in some cases probably try to optimize the energy consumption of the whole data center. So if we zoom on that server, so each physical server is a type 2 hypervisor, where on top of that we can create multiple VMs, and we can have our containers running either within the host operating system or within the VMs that we have. And also there is a net data agent that where you can see here that exposes all the hardware statistics about utilization for CPU, RAM, etc. So now some concerns that are raised when we measure power on the software level is how performance of the overall system is affected when we use software that is intended for estimating the power consumption of a process. So we want it to be as light as possible. And of course, we want the software to return accurate results about power consumption. And of course, another concern is what restrictions are imposed on the hardware, whether it is compatible with all types of CPUs or just for a specific type of CPU architecture. So we looked in the literature and we identified some tools that are intended for this purpose. All of them, they are doing pretty much the same thing, although some tools are following a different way in order to achieve this. Of course, there are other tools in the literature, but for now, we have been able to get the code for the first three. The first two are open source. And for the third one, we have communicated with the initial author who was willing to share the code with us. And for your information, we have been able to deploy Smartwatch on our infrastructure, which you saw on the previous diagram. Most of them, they are based on a module that is provided by modern Intel CPUs called the RAPL, and it exposes the energy estimations for CPU and DRAM based on some performance counters that are generated operating system. And there is another category of work where they are based on QR machine learning techniques, and more specifically WhatsApp. It's making use of a neural network in order to be able to estimate the energy consumption of a container. So we made a comparison of the aforementioned tools based on some characteristics, whether each tool is open source, whether it supports measurements for VMs, containers, and containers within VMs, whether there is documentation, whether the tool is already Dockerized, and whether it's architecture specific. And we also looked in the literature for some workloads that we can make use in order to evaluate the aforementioned tools. We started with stress command that is provided in Linux and gives you the opportunity to stress different hardware components like CPU, memory, disk, and then we moved to slightly more advanced benchmarks. More specifically, ML pair inference benchmark provide a set of machine vision workloads and a language translation workloads. So far, I have been able to run image classification from machine vision library and the language translation that is based on the GNMT model provided by Google and used for Google Translate. And we found a few other HiBench has a set of benchmarks ranging from micro benchmarks to more advanced machine learning benchmarks and streaming application. And Yahoo Bench is purely intended for streaming applications like Apache, Spark, Storm, or Flink. And I'm providing some preliminary results for the translation workload. So they are just preliminary results. On this diagram here, you can see the CPU, the total power consumption, the actual power consumption actually for the time that we run the workload and measure through the PDU. You can see for the period that we executed the workload, the total energy consumption raised from 150 watts to 300 watts, which is double the idle value. And on this diagram, you can see the CPU utilization of different applications for the same period that we executed the workload. So on top with the yellow line, it's the CPU overhead of the workload itself, which is run on a Docker container that creates a Python environment within the container. With the green line, it's the CPU overhead of the kernel, because in this case, we are using a machine learning library called MLCube, which communicates with the kernel. That's why we can see the increase in the kernel, in the kernel dimension. And on the bottom, the slight decrease corresponds to the VMs, and more specifically, this goes for the hypervisor that is responsible to create VMs in the system. And for some reason, which is not clear yet, we can see an increase for the time that we executed the workload in a container. And on this diagram, you can see the power estimation for processes based on the Smartwatch tool that we deployed on our infrastructure. So Smartwatch by default it tries to estimate power for either containers or virtual machines. A few things to note on this diagram is it's a few weaknesses that are that have been observed for Smartwatch. You can see a gap here, and the reason that there is a gap here is that because Smartwatch was not able to identify in real time that the container was closed. So after the end of after we stopped the container, and was keep showing some results due to the way Smartwatch is working. So I had to manually restart the Smartwatch service in order for the measurements to go back to the idle state. Something else that it's worth checking on this diagram is that the increase on the energy consumption reported here is not proportional to the actual consumption that we observed through the PDU, and that is why Smartwatch by default checks a specific scene group that belongs to virtual machines and containers, and was not able, if you check on this diagram here again for CPU, was not able to identify the increase for the workload itself, because in the OS it is reported as a Python process instead of a Docker process. So I believe that Smartwatch can only see the small increase to the VM's dimension over here, and the measurements here are based only on that. I believe that there is a workaround for this. If you say to Smartwatch, for example, to explicitly track a specific process ID, but it's something to try for sure. And probably Smartwatch is not the ideal tool in our case in order to get estimates for VMs and containers. And finishing with some future work. Moving on, we would like to run more workloads and try to see how the power consumption varies. Even for the same workloads, we can try to run them with different configuration and examine the variation in power consumption. Then we can compare the various tools against each other and see which one is the more appropriate in our case, that gives the most accurate results based on the real power consumption that we can get. We can, once we have this information, we will be in a position to create a model for energy efficient placement for a data center like ours, and possibly we can even extend this model in order to take into account the energy production that we have on our DC, since I don't believe currently there are a lot of works that they are taking into account the energy production. And another possible work will be to examine some pricing models for edge data centers. like ours. Thank you for your attention. In case you have anything you would like to discuss, feel free to.
Thank you very much, Michalis, for your presentation.
If I have some complementary slides about another project that we have, in case you are interested, in our lab, which we can make use moving on. Basically, another student is working towards automating the whole benchmarking operation. So pretty much the work that is done is an extension of the NAV system that you have seen before, in order for the users to submit the benchmarking details, and the system in an automated way to execute them on our cluster. And then we will be in a position, of course, to collect our results for energy consumption in a more automated way and further analyze them. Yeah. Any questions or anything you would like to discuss with me?
I have one topic I want to discuss with you.
Yes.
I already use the Fogify, but I'm not sure currently Fogify support for this estimation, like
Yes.
the power estimation. Is currently
Yes.
it have?
Actually, yeah, Fogify, it's an emulator specifically.
Yeah, the emulator.
For
The
HTML. Yeah. Actually, there is another researcher, the creator of Fogify. It's in our lab, and of course, we can make use of Fogify in order to simulate the energy consumption of federated data centers. So, in case we have a scenario, for example, in a city, and let's say we add like edge data centers, like the ones I mentioned here, all around the city. In a scenario like this one, ideally, we can use Fogify in order to simulate the communication and the power production all over the city, and then run our workloads on Fogify. And this will provide us a better idea of what happens in greater scale, for example. So yeah, so this is something that we discussed before with the author, and probably something to consider for the next steps.
Yeah, okay. I just added because if it already supports, I will use this for my implementation because it sells a lot of money to buy the some kinds of device to
yes,
to
of
test.
course, yeah.
Okay, just let me know if everything available. I will use it. Thank you,
okay.
Michalis.
Thank you, Ha, for your question. Thank you. Anything else that you would like to add?
I think if there are no more questions, then we can thank Michalis for his very nice presentation. And I think this is the last seminar of the year, so I guess see you next year for the next round of seminars.
Okay, see you.